Hello guys, welcome back to my YouTube channel. I hope you all are doing extremely well. So, myself Shaurya Modi, and today we are going to study practical statistics for data scientist. So, you might be aware with this book, Practical Statistics for Data Scientist by its publisher is O'Reilly. So, it looks something like this. You can easily get the book PDF on the internet. So today we are going to study chapter 1, 2 and 3 of this book so that we have an uh, good knowledge till A/B testing and all, which is needed for product and data related roles. We won't be diving into chapter 4, 5 and 6 because these chapters are related to machine learning and all. Today we are covering only the statistics part. We might do these chapters in future, but now we are focusing on chapter 1, 2 and 3 only. So the chapter 1 is exploratory data analysis, chapter 2 is data and sampling distributions, chapter 3 is statistical experiments and significance and testing. So first you can easily get this book by just writing practical statistics for data scientists PDF. You can easily get its PDF on the internet. So if we will focus only on these three chapters. Chapter 3 is statistical experiments and significance testing. So we are not going to directly read the content of the book like the theory and all, uh, like the theory, whole irrelevant theory and long theory which is written in the book, like elements of structured data. Like I myself have broken down, I have myself have made the notes of the topics in the book in form of a Jupyter notebook. So here is that Jupyter notebook. Yeah, it's the Jupyter notebook of the chapter 1. I myself have made the I myself have taken all the topics from the book and not directly written the theory from the book but have made its notes, then presented it here so that it's easier for all of us to understand and get only the relevant information and knowledge from the book. So without further ado, let's get started with chapter number 1. So practical statistics for data scientists. So here is the index as well. I will provide this Jupyter notebook in my GitHub as well, whose link will be in the description below. So let's start with the chapter 1, exploratory data analysis. The baseline. EDA is the mandatory first step to check data health, shape and structure before any modeling or A/B testing. The mechanics. EDA uses summary stats like medians, quantiles, and simple visuals like box plots, scatter plots to expose the hidden patterns fast. The business value. EDA instantly catches anomalies and pressure test assumptions before investing heavy engineering time. Uh, Topic number 1, elements of structured data. The engineering goal. All the messy, unstructured data must be forced into structured tabular format before you can learn in the tabular format like rows and columns before you can run SQL or pandas operations. The code taxonomy. So the structured data is of two types, numeric and categorical. Numeric data is further divided into two parts, continuous and discrete. Continuous. Example, app load, latency, revenue, etc. Discrete. Daily active user counts, number of clicks. Categorical. Categorical data is further divided into two parts, binary and ordinal. Binary, as the name suggests, it has just two output like yes or no. Ordinal data, example CSAT or NPS ratings from 1 to 5 where order matters. CSAT stands for customer satisfaction rating, like whatever ratings we get, that we have to rate 1 to 5. That's a type of ordinal data. NPS ratings, what does it mean? Let me see. NPS ratings, Net Promoter Score, measures customer loyalty and satisfaction. Yeah, it's similar to CSAT, where the where we have ratings from 1 to 5 where the order matters. The why it matters. Why data must be converted into structured tabular format. Why it matters. Explicitly declaring data types in pandas isn't just a theory. It dictates memory efficiency, prevents computational errors, example trying to average zip codes, and determines which visualizations will actually work. Explicitly declaring data types. Okay. So, explicitly declaring data types in pandas isn't just theory, it dictates the memory efficiency, prevents computational errors, and determines which visualizations will actually work. Second topic, rectangular data and data frames. The standard anatomy. A data frame is a two-dimensional matrix that runs modern analytics. In business terms, rows are records, example individual users, daily transactions or warehouse shipments, and columns are features like subscription tier, customer tenure, order value, etc. Features versus target. If you are building a model or A/B test, you must split your columns mentally. The target is what the target or outcome is what you are trying to predict. For example, did user churn 1 or 0? The features are the variables you use to make the prediction. The power of index. In pandas, the index isn't just a row number, it's the backbone of performance. Setting the correct index, like user ID or timestamp, is mandatory for executing fast and complex SQL style joins and time series aggregations without crashing your pipeline. Okay, here is then an example of a typical data frame format. So data is in rows and columns. So columns are features, for example, currency, seller rating, duration and day, etc. And this competitive column is the target or outcome which you are trying to predict. Okay, so is this pricing competitive or not? 0, 0, 0 or 1. Okay, this is an example of a typical data frame format. Third, estimates of location, central tendency. Mean, the sum of all values divided by number of values is the average. Sum of all values divided by number of values is the mean. So here is its formula. We sum all the values and divide by number of values. Weighted mean, the sum of all values times a weight divided by sum of weights. Okay, here is the formula. W1 WIXI upon WI. Median 50th percentile, the value such that one half of data lies above and below it. Percentile, the value such that p% of data lies below. Weighted median, the value such that one half of the sum lies above or below the sorted data. Trimmed mean or truncated mean, the value of the average of all values after dropping a fixed number of extreme values is the trimmed mean. Robust, robust data which is not sensitive to extreme values. Outlier, a data value that is very different from most of the data is known as the outlier or extreme value. Okay, outlier, a data value that is very different from most of the data. The mean versus median trap. The mean average is highly sensitive to outliers. For example, a few massive enterprise whale accounts will falsely inflate your average revenue per user. The median is robust. It ignores extremes and tells you exactly what the typical user or transactions look like. Cleaning noisy pipelines. Trimmed mean. Tech data is inherently noisy. Bot traffic, QA test accounts, tracking glitches, etc. A trimmed mean. For example, dropping top, bottom, and top 5% of data is how analysts establish a clean baseline without manually hunting down every single anomaly. Volume adjusted matrices, weighted mean. You cannot simply average averages. If you are calculating the overall conversion rate across 5 different marketing channels, you must weigh the mean by the total traffic volume of each channel. Or low volume channel will severely distort your global metric. You cannot average the averages. If you are calculating the overall conversion rate across 5 different marketing channels, you must weigh the mean by total traffic volume of each channel. Okay. Or low volume channels will severely distort your global metric. The dual nature of outliers. In standard product analyst in standard product analytics, outliers are a nuisance you filter out. In anomaly detection, example credit card fraud modeling, server latency spikes, the outliers are the product and the mean just serves as the baseline to trigger alerts. In anomaly detection, in standard product analytics, outliers are nuisance you filter out. In anomaly detection, like credit card fraud modeling, server latency spikes, the outliers are the product and the median just serves as the baseline to trigger alerts. So here is an example question which we are going to do to understand the topic of estimates of location properly. So here is question number 3.1. Location estimates of customer lifetime value. So here is the question to explain this topic, estimates of locations, central tendency. Okay. Leadership often asks a deceptively Leadership often asks a deceptively simple question. Okay. The business problem or question. Leadership needs to determine average lifetime value of a customer to accurately forecast revenue and set strict customer acquisition cost budgets for marketing team. We must answer a critical financial question. What is the true baseline value of a typical customer? And are extreme outliers artificially inflating our acquisition budgets? So, leadership often asks us a very simple question: what is the average lifetime value of our customer? They need this number to set strict customer acquisition cost or CAC budgets for marketing team. But there is a massive trap here. If extreme outliers are artificially inflating our average, marketing will overspend to acquire new users, burning through our cash runway. Today we are going to use Python to find true baseline values of a typical customer. Okay, data context or setup. So to show you exactly how this happens, we are going to generate a simulated retail transaction dataset first. First, we will calculate total spend per customer, their CLTV, by multiplying the quantity of items by their unit price, filtering out any cancelled orders. But here is a catch. Real e-commerce data is almost never a perfect symmetrical bell curve. We are going to intentionally build a heavily right skewed data set. It will contain thousands of normal everyday retail shoppers spending about $50 mixed in with a tiny handful of B2B wholesale whales dropping around $10,000 or more at a time. Okay, let's dive into the code to see how these whales completely distort our math and which statistical matrices we should use instead to find the truth. Okay, so let's start coding. Import import pandas as pd, import numpy as mp, import numpy import numpy import numpy as np from scipy, import stats, import matplotlib dot pyplot as plt. Okay, so first simulate the raw e-commerce transaction data. Simulate the raw e-commerce transaction data. np dot random dot seed 42. Normal retail shoppers, thousands of low value orders, retail underscore qty equals np dot random dot random integer 1 comma 5 comma size equals 9500 equals 9500. Retail underscore price is equals to np dot random dot rand dot uniform 10 comma 50 comma size equals 9500. B2B wholesale whales. A few massive orders. Okay. B2B QTY equals np dot random dot rand int 50 comma 500 comma size equals to 500. B2B price equals np dot random dot uniform 100 comma 500 comma size equals to 500 equals to 500. Raw data, raw underscore data equals pd dot data frame customer id np dot concatenate np dot random dot rand int customer id concatenate random int 1 to 8000 comma size equals to 9500 comma np dot random dot rand int 8001 to 8200 comma size equals to 500 comma quantity np dot concatenate retail underscore qty comma b2b qty b2b quantity comma unit price np dot concatenate retail price comma b2b price b2b price comma status np dot random dot choice completed comma cancelled, comma, size equals to 10,000, comma, p equals to 0.95 to 0.5. Okay. So let's close this raw data frame which we have created, curly bracket, parenthesis. Now let's start with data processing and feature engineering. So we have now created our data set. Now let's move to the next step, data processing and feature engineering. First we filter out the cancelled order. Filter out cancelled orders. Valid orders equals to raw data where status is completed, where status equals completed dot copy. Then we create the order value feature, create the orders value feature, valid orders, order value, order underscore value equals to valid orders quantity into valid orders unit price, valid orders unit price. Then we group by customer ID to get total spend, group by customer ID to get total spend CLTV, group by customer ID to get total spend CLTV, customer spend equals to valid orders dot group by customer ID orders value dot dot sum dot reset index customer spend dot rename customer spend dot rename columns equals to order value as total spend, total value as total spend, total spend in place equals to true. Then finally we calculate the location estimates. Calculate the location estimates mean spend equals to customer spend total spend dot mean median spend equals to customer spend total spend dot median trimmed mean spend equals stats dot trim mean customer spend total spend total spend comma portion to cut 0.1 comma portion proportion to cut equals to 0.1 print CLTV location estimates print f mean the trap dollar mean spend equals to comma dot 2 f print f trimmed mean the core 80% the core 80% trimmed mean spend dot 2 f print f median the reality median spend comma dot to f backslash n. Now finally the executive visualization. Okay, hashtag 4 executive visualization plt dot figure fig scale equals to 10,5 tag plotting a log scale histogram due to extreme skewness. Log scale histogram due to extreme skewness. Plt dot hist np dot log 1p customer spend total spend bins equals to 50 color equals to hashtag 2c3e50 edge color equals to white edgeclor edge color equals to white. Then we add location estimates as vertical lines using distinct colorblind friendly palette. Then we add the location estimates as vertical lines using a distinct line plt dot axv line np dot log 1p mean spend comma color color equals stack c 0392b line style equals to dash line width equals 3 label equals to mean. Plt dot axv line np dot log 1p trimmed mean spend, comma color equals to hashtag D35400, comma line style as double dash, line width 3, label as trimmed mean. Plt dot v line plt dot median spend, color as hashtag 2980 b9, line style as a single dash, is median, label median. Okay, so finally plt dot title customer lifetime value log scale with location estimates, font size 14, comma font size equals to 14, plt dot xlabel log of total spend in dollars, comma font weight equals to bold, plt dot ylabel frequency number of customers plt dot legend log equals upper right, plt dot grid axis equals to y, comma line style equals to double dash alpha equals 0.4, plt dot tight layout plt dot show. Okay, unterminated string literal at line number 33. Line number 33. Customer spend. Okay. Unterminated string literal. Data line number 49. PLT dot hist. Okay. Double. Finally, let's wait for the output. Valid orders is not defined. Valid order is not defined. Line number 30. Valid orders. Let's run this code. Invalid format specifier. PLT location estimates. PLT location estimates F mean the trap. Invalid format specifier. Format specifier missing precision. Number 43, comma, comma. PLT dot fig scale. Number 47. Figure dot set got an expected argument fig scale. Fig size. Fig size. Finally, we have the output. So first we generated a random data. Let me show you our random data as well. Okay, so finally, here is the table which we created, which has customer ID, quantity, unit price, and status. I have viewed only the top 5 uh, rows, so all the status are completed, but the total number of rows are 10,000. It has the status equal to cancelled also as well. So let's view our output again. So here is our beautiful output. So the random data which we created had the mean of 7,247, okay, which is very high. So here is the line of mean. The trimmed mean, the core 80% is around $118, which is very less compared to our mean, and the median is $108, the reality. Okay, when we run through the numbers on our transaction data, the standard mean customer spends shows around roughly $1,500. uh, but if we blindly report this number to marketing team, they will drastically overspend on acquiring new users, burning through our cash runaway. The mean is heavily distorted by distribution trap. A small handful of wholesale B2B buyers making making massive $10,000 purchases, but dragging the math average sky high. To find our true baseline, we look at the median, which sits around $105. This is our operational reality. Half of our entire user base spends around $108 or less over their lifetime. So we calculated a 10% trimmed mean, which sits around $118. This metric acts as a great middle ground, statistically filtering out the extreme wholesale whales while still capturing the value of our high tier normal retail shoppers. Moving forward, we s- we se- moving forward when setting baseline customer acquisition cost budgets for standard digital campaigns, we must anchor our financial models to the median, absolutely not to the mean. Okay, so the final output of this exercise was that we must not only look towards the mean for getting the any data, because some outliers and big customers who make uh, who spend lot of money compared to normal users can heavily skew the data. We must always rely on trimmed mean or median to get the actual cost which which the customers on an average are spending. So by this exercise we can give the correct customer acquisition cost to our marketing team. Think of it, if we had given 7,247 as a cost to the marketing team, they would certainly overspend on acquiring the new users, but the actual customer acquisition cost must stay around 108 to $118 to not overspend the money to acquire the new customers. So let's move to the our next topic, estimates of variability, dispersion. estimates of variability, dispersion, deviations, errors or residuals. The difference between observed values and the estimate of location is known as the deviations. Variance, mean squared error. The sum of squared deviations from the mean divided by n minus 1, where n is the number of data values, is variance. Standard deviation, square root of variance, is known as standard deviation. Mean absolute deviation, the mean of absolute values of the deviations from the mean. Median absolute deviation from median, median of absolute values of deviations from median. Range, the range between largest and smallest value in a dataset is the range. Order statistics, metrics based on the data values sorted from smallest to biggest. Interquartile range, IQR, the difference between 75th percentile and 25th percentile. Variance and standard deviation are the baseline matrices for spread. Standard deviation is preferred because it is on the same scale as the original data, example dollars or minutes. However, because the math squares the deviations, a single massive outlier will violently distort the result. Mean absolute deviation, an alternative that takes absolute value of the differences instead of squaring them. It is less sensitive to extreme outliers than standard deviation, but because it still relies on the mean, it remains vulnerable to highly skewed tech data. Mean absolute deviation, the ultimate robust metric for spread. It calculates the median of the deviations from the median. For example, if a server logging errors create a 10-hour session uh, creates a fake 10-hour session length, MAD, ignores it completely, while standard deviation would trigger false alarm. Interquartile range measures the spread between middle 50% of your dataset, 75th percentile minus 25th percentile. This defines your core customer base, stripped of both the low performing and high performing extremes. Order statistics and percentiles, the gold standard for tech and operations. Sorting the data and finding the 99th percentile explicitly isolates your top 1% worst scenarios. Critical for tracking latency SLAs and preventing premium user churn. So here is an example to understand variability estimates. To understand estimates of variability. So here is an example, variability estimates of order values. Okay, if you are running operations for a e-commerce brand, predictability is everything. You need to know exactly how much inventory is going to leave the warehouse and how many staff members you need to pack those boxes. But if your daily basket size sizes seem to fluctuate widely, forecasting becomes completely impossible. Today, we are going to look at the math behind the revenue volatility to answer a critical operational question. Is our daily revenue actually volatile? Okay. Is our daily revenue actually volatile, or are a few extreme massive orders mathematically distorting how predictable our everyday business really is? So, the setup. To diagnose this, we are going to jump into Python and stimulate a highly realistic e-commerce dataset, focusing on one core metric, order value. Just like real life, this won't be a perfectly smooth dataset. We are going to intentionally build a highly right skewed distribution. The vast majority of data will represent standard predictable retail orders. But to test our matrices, we are going to inject a small handful of massive B2B wholesale spikes into the mix. We will then look at how these extreme outliers completely break standard volatility matrices like standard deviation, and I will show you exactly which robust matrices you should be using instead to find the truth. Okay, so let's start with writing the code. Import pandas as pd, import numpy as np from scipy.stats, import median absolute deviation, median abs deviation. So first simulate the order data. Retail base plus wholesale outliers. Wholesale outliers. np dot random dot seed 42. Retail orders equals np dot random dot normal lock equals to 50 comma scale equals 15 comma size equals 9500. Wholesale orders wholesale orders equals np dot random dot normal lock equals 5000 comma scale equals 500 comma size equals 500. So we create the data frame df equals to pd dot data frame order value order value np dot concatenate np dot concatenate retail orders comma wholesale orders. Second, standard deviation, highly sensitive to outliers. Highly sensitive to outliers. std.dev equals df order value dot std interquartile range or IQR, spread of the middle 50% of orders. IQR IQR equals to IQR equals to DF order value dot quantile quantile 0.0.75 minus df order value dot quantile 0.25 hashtag 4 median absolute deviation or MAD, the most robust spread metric. MAD equals to median absolute deviation df order value print print order value variability estimates. Print f standard deviation the illusion as std underscore dev comma dot to f dot to f. Okay, print f interquartile range or IQR, the core 50% spread as dollar IQR comma dot 2f print f mean absolute deviation, the reality as dollar MAD, comma dot 2f. Okay, when we run the code, yeah, it's fine. Okay, so if we just look at the standard deviation, our order values fluctuate by over 1082 rupees or 1082 dollars. If we had if we hand that number to the supply chain team, they will panic and overstock the inventory to buffer against the massive volatility. But the math is lying to us. When we calculate IQR and the MAD, which are robust against the extreme outliers, the actual spread drops down to just $21 and $10. The extreme volatility isn't coming from our core user base. It is isolated entirely to the dozen of B2B wholesale buyers making massive infrequent purchases. Our everyday customer is actually incredibly predictable. Moving forward, we should forecast on our main warehouse inventory based on these robust matrices, not the standard deviation, saving us a massive amount of capital in unnecessary buffer stock. I will show you the data frame as well. df df dot head 5. So here is our uh, data frame which we have created. So let's view the full data frame first. So here are the 1000 rows of the data frame. So as you can see, the data frame has various order values from 57, like 57, 47, 59, 72, etc, etc, to all the way to 5600, 4000, 4600, etc, etc. So we we calculate the uh, order value variability estimates, like what will be the variability in order value. So if we so the supply chain team, uh, so operations need to know how predictable our revenue and inventory drawdowns are. If basket sizes fluctuate wildly every day, warehousing staff warehouse staffing and inventory forecasting becomes impossible. We need to answer a critical operational question: is our daily revenue actually volatile, or a few extreme orders artificially distorting our perceived predictability? So, our daily revenue is very predictable, as you can see from the data. So, our everyday customer is actually very predictable. Moving forward, we should forecast our main warehouse inventory based on these robust matrices like IVR and MAD, not the standard deviation, saving us a massive amount of capital in unnecessary buffer stock. Let's start with our next topic, exploring the data distribution. Okay, so let's move to our topic number 5, exploring the data distribution. Boxplots. The anomaly radar. A box plot is a visual manifestation of your robust matrices. The box, the box is your interquartile range, the middle 50% core users. The line inside is the median, and the whiskers show the boundary of the normal behavior. Any dots outside the whiskers are mathematical outliers in a tech context. These are your server latency spikes, bot traffic, or VIP enterprise whales that require immediate investigation. Histograms mapping the terrain. While a mean or median gives you one number, an histogram shows you the entire landscape by grouping the data into equal sized buckets or bins. It instantly answers the business questions like: are our delivery times tightly clustered across 15 minutes? Are our delivery times tightly clustered around 15 minutes? Or do we have a massive fat tail of deliveries taking over 45 minutes? Equal size versus equal count bins. Understand the difference of segmentation. A histogram uses equal size bins. Histograms mapping the terrains. While a mean or median gives you one number, a histogram shows you the entire landscape by grouping data into equal sized buckets or bins. It instantly answers the business questions like: are our delivery times tightly clustered around 15 minutes? Or do we have a massive fat tail of deliveries taking over 45 minutes? Equal size versus equal count bins. Understand the difference for segmentation. A histogram uses equal sized bins. For example, grouping users by spend 0 to 10, 10 to 20, etc. Which means some bins might be empty. Percentiles or quantiles use equal count bins. Grouping users so exactly 100 users are in each bucket, which changes the dollar range of each bucket. Equal size versus equal count bins. Okay. The skewness reality. In textbook statistics, everything is a perfect bell curve, normal distribution. In SaaS or quick commerce, data is almost always right skewed. The skewness reality. In textbook statistics, everything is a perfect bell curve, normal distribution. In SaaS and quick commerce, data is almost always right skewed. A massive cluster for free tiers or low spend users on the left, with a long tail of high value users dragging out to the right. Histograms instantly reveal this skew, proving why you must use the median instead of the mean. Okay, so here is the question to understand the topic: exploring the data distribution. Example question 5.1: Diagnosing API latency and enterprise SLAs. Okay, so let's read the question. Okay, the hook explaining the business problem. When you are selling enterprise software, platform performance isn't just a technical metric, it is a financial and legal obligation tied to the strict service level agreements or SLAs. Today we are going to help our operations and engineering teams answer a critical diagnostic question: is our platform actually providing a consistently fast experience for the vast majority of our users? Or are a few catastrophic system timeouts completely masking the true performance issues? Is our platform actually providing a consistently fast experience for majority of the users? Or are a few catastrophic systems timeouts completely masking true performance issues? Okay, the setup explaining the dataset. To figure this out, we are going to jump into Python and stimulate thousands of requests pulled directly from enterprise tech traffic logs. Our core metric for this analysis is API response latency measured in milliseconds. Okay. Just like real world production environment, this data is not going to be perfectly symmetrical. It is going to be heavily right skewed. The vast majority of our stimulated requests will process quickly and smoothly. However, we are going to intentionally build in a critical tail for the requests that experience severe lag. We will then look at exactly how to use percentiles and box plots to expose these hidden SLA violations that a standard average won't completely ignore. So let's start by writing the code. Import pandas as pd, import pandas as pd, import numpy as np, import matplotlib dot pyplot as plt, simulate realistic right skewed API latency data, np.random.seed42, simulating a mix of normal traffic and slow API latency and slow long tail requests. Normal traffic equals to np.random.normal log equals 150, comma scale equals 40, comma size equals 7000. Heavy traffic equals np.random.normal log 150, log 350, comma scale equals 80, comma size equals 2000. Timeout spikes equals np.random.exponential scale equals to 600, comma size equals 1000. Latency underscore data equals np.concatenate np.concatenate normal traffic, heavy traffic, comma timeout spikes. Ensure no negative millisecond values. Latency underscore data equals to np dot clip latency data, comma 15, comma none. df equals to pd dot data frame API latency milliseconds latency underscore data. Number 2, calculating percentiles the SLA matrices. Calculating percentiles the SLA matrices. The SLA matrix P05 equals df API latency ms dot quantile dot quantile 0.05 P25 median P75 P95. P25 equals to API latency ms quantile 25. Median equals API latency ms dot quantile 50. P75 equals API latency ms quantile 75. P95 equals API latency ms quantile 95. So print API latency SLA matrix print f fifth percentile fastest P05.0 f ms. Print f 25th percentile P25 dot 0 f ms. Print f median as median dot 0 f ms. Print print 75th percentile as P75 0 f ms. Print 95th percentile as P95 ms. Visualizing a box plot. an executive summary. So 3, a visualizing with a box plot. plt dot figure fig size equals 10 comma 5. Creating a horizontal box plot for readability. Box equals plt dot box plot df API latency ms comma vertical equals false comma patch artist equals true comma okay. Box props equals dict face color equals uh, I think it will run just fine without giving the color and all. Let's see. plt dot title enterprise plt dot title enterprise API response latency SLA diagnostic comma font size equals 14 plt dot title enterprise font size 14 comma font weight equals what font weight did we give before? Font weight equals to bold. Font weight equals to bold. plt dot x label latency in milliseconds comma font weight comma font weight equals bold. plt dot y ticks okay. This hides y-axis ticks as there is only one category. Okay. So annotating the box plot, plt.axv line, median, comma color equals hashtag E74C3C, comma line style dash dash, comma alpha equals 0.6, comma label median baseline, plt comma axv line p95, p95, color as same, line style same, line width 2, line width equals to 2, label is p95 SLA threshold, p95 SLA threshold, plt dot legend, plt dot legend lock equals upper right, comma plt dot grid axis equals x, comma line style equals dash dash, comma alpha equals 0.4, plt dot tight layout, plt dot show, plt dot show, plt dot xv line bracket was never closed. Okay, now it is closed. Timeout spikes is not defined. Latency data, latency data, timeout, line number 13. Timeout spikes was never defined clearly. Time out, latency data df equals to latency data. Okay, finally we have the output. So when we evaluate our the fifth percent API latency SLA matrices, fifth percentile is 85 milliseconds, 25th percentile is 131, and similarly the median 75th percentile and 90th percentile. Okay. When we evaluate our infrastructure health by looking at the percentiles, the median latency sits at the healthy 168 milliseconds. However, the variability across the platform is massive. The fastest 5% of requests clear our servers in just 85 milliseconds. But the 95th percentile hits roughly 503 milliseconds. Okay. If we are pitching to the enterprise clients who require real-time data processing, this massive lag of 500 milliseconds, this 500 millisecond lag at P95 level is a massive churn risk, major churn risk and explicit violation of standard SLAs. If you look at the box plot, the physical blue box represents the interquartile range. Okay, the middle 50% of our traffic. This is our core operational baseline, showing that vast majority of our requests processes safely between 131 milliseconds and 250 milliseconds. However, all those individual dots stretching to the right represents the catastrophic outliers. We cannot just look at the median. We must immediately allocate engineering resources to investigate the tail end volatility before it damages our enterprise contracts. So we have got this data. What we needed? We must answer a critical diagnostic question. Is our platform providing a consistently fast experience for a vast majority of the users? Or are catastrophic system timeouts masking true performance issues? So based on the data, PXV line grid. So here is our grid. So yeah, we can see the median lies around 168 milliseconds, which is around here, and 95th percentile is around here, 503 milliseconds. Okay, these all individual dots stretching out to the right represent catastrophic outliers. We cannot just look at the median. We cannot just look at the median. We must immediately allocate engineering resources to investigate the tail end volatility before it damages our enterprise contract. So we can conclude that it is an catastrophic system timeouts masking our true performance issues, or are catastrophic system timeouts masking true performance. Yeah, it is truly an performance issue. We must allocate our engineering resources to fix this before it damages our enterprise contracts. So let's move to our next question. So let's start with our example question number 5.2, visualizing revenue segmentation and distribution. So the hook, explaining the business problem. Before sales leadership can design next year's compensation plans, crave out territories, and set realistic quotas, they have to understand the true shape of our revenue. Today we are going to use the data to answer a critical strategic question. Is our business driven by high volume of standard predictable contracts, or are we dangerously resilient on a few massive unpredictable whale accounts? So this setup explaining the data set. To visualize this, we are going to jump up into Python and simulate a dataset of 5000 active enterprise contracts. Our primary metric here is annual contract value, or ACV, measured in US dollars. to make this as realistic as possible. We aren't using perfectly even data. We are going to generate a heavily right skewed log normal distribution. This means vast majority of our simulated contracts. Okay, this means the vast majority of our simulated contracts will sit right in that standard 50,000 range. But we are going to deliberately build in a long tail of rare whale contracts reaching almost 5 lakhs dollars or above. Let's dive in and see how we can use frequency tables and histograms to instantly expose the true shape of this revenue. Okay, let's start coding. Okay, so let's start. Import pandas as pd. Import numpy as np. Import matplotlib dot pyplot as plt. So set seed for reproducibility. Reproducibility. np dot random dot seed. np dot random dot seed 10 1. Simulate 5,000 enterprise contracts. Enterprise contracts. Enterprise contracts. Right skewed. Most contracts are around 30k USD to 50k USD. But a few whales are 500k plus. Okay. Simulated ACV equals np dot random dot log normal mean equals 10.5 comma sigma equals 1.2 comma size equals 5,000. ACV data equals pd dot data frame contract value USD. Contract value USD as simulated ACV. Tag number 2, create the frequency table pandas.cut. We divide the massive range into 10 equal sized bins. Bind revenue equals pd dot cut acv underscore data as contract value usd comma bins equals 10. Frequency table equals bind revenue dot value counts dot sort index. Print enterprise ACV frequency table print print frequency table. Then we plot the histogram AX equals ACV underscore data underscore contract value USD dot plot dot hist bins equals 30 comma fig size equals 8 comma 5 comma edge color equals blue ax dot set x label as annual contract value as annual contract value ACV in USD. AX dot set Y label as number of enterprise accounts. AX dot set title as distribution of enterprise revenue. Distribution of enterprise revenue. Then formatting the x-axis to show dollar amounts clearly. AX dot x-axis x-axis dot set major formatter plt dot function formatter lambda x as lock comma format int as x plt dot show. Invalid syntax. ex dot measure ex dot set measure formatter plt dot lambda x comma. Okay, name x is not defined. Dot int. This is not defined. Anyways, if it is not working, let me remove it. Okay, plt dot show. Finally, we have an enterprise annual contract value frequency table. So we can see that most of the accounts lie in this range. Okay, from negative 2000 to uh, 2,76,000 or 276K. And what about this? 2,76. So it is 2,76K and it is around 27 lakhs. Yeah, it is 27 lakhs and it is 2,76,000. So we have an account contract value frequency table. So here is the contract value in USD. So you can see from the first row, you can see minus 2000 to 2,76,000 are in USD, from $2,000 to $2,76,000. We have 4,794 accounts. Similarly, in the next range, we have 156 accounts, and so on. And you can see the distribution as well. Annual contract value, ACV, and number of accounts. Okay. So you can see the annual contract value as well. Mm, Plot the X label. Okay, we had not formatted the x-axis to show dollar amounts clearly. Okay, if we do this now, lambda x is not defined. It's not working. That formatter, no, format int. Anyways, let's not spend much time in showing the x-axis, in formatting the x-axis to show dollar amounts. It's kinda understandable. Okay, so what we can understand from this data, what we needed to answer, is our revenue driven by high volume of standard sized contracts, or we are heavily reliant on few massive unpredictable whale accounts. So we have got this frequency table. Okay, when we group our 5,000 enterprise contracts into frequency table and then visualize them in the histogram, we see a massive right skew in our revenue distribution. The towering bar on the far left shows our operational reality. The vast majority of our sales volumes comes from standard contracts in the range of in the range from 0 USD to 2,76,000 USD range. However, look at the long tail dragging out to the right. Those are our whales, rare massive contracts exceeding more than uh, many lakhs of dollars. For example, one whale account is in the range of 24 lakhs USD to 27 lakhs USD. So strategically, this means we cannot use a one size fits all sales quota based on a mathematical average. If we do, our volumes based on reps will fail, and our strategic reps will blow past their targets with a single deal. We need to split the sales organization into two distinct motions. A velocity team optimized for churning through standard around 270,000 around 250,000 K deals, and a strategic enterprise team dedicated entirely to hunting and closing that long tail outliers. So, uh, is our revenue driven by high volumes of standard sizes accounts? Yes. Or are we? No, we are not heavily reliant on few massive unpredictable whales account. Okay, we need to split the sales organization into two distinct motion. A velocity team optimized for churning the standard accounts that are our bulk of our accounts of our contracts, and a strategic or enterprise team dedicated entirely to hunting and closing the long-tailed outliers. So let's move to our next topic, exploring binary and categorical data. Categorical summaries, bar charts and mode. So let's start with the next topic, exploring binary and categorical data. Categorical summaries, bar chart and mode. When evaluating categorical data, example device type, region, subscription tier, etc., we don't look at the means or medians. We look at the proportion and frequencies. The mode identifies the most frequent category. Bar chart is the standard visual to compare these frequencies. Bar charts versus histograms. Do not confuse the two. Histogram plot the continuous distribution of a single value of a single numeric variable, bar touches. Bar charts plot the counts of distinct separate categories, bar have gaps. Crucial rules. Never use pie chart in business presentations. Humans are terrible at visually comparing slice angles. Always use bar charts. The power of expected value. This is the foundation. Uh, 90%. Okay, the power of expected value. This is the foundation of consulting case studies and tech monetization. EV, expected value, is the weighted mean where weights are probabilities. If a new feature has a 10% probability of generating 500 US dollars and a 90% probability of generating $0, the EV, expected value of that feature, is 50. So this is how you calculate the average financial yield of a user action when the outcome is uncertain. Binning continues to categorical. Sometimes the best way to analyze numerical data like exact date, exact age 24, 31, 45 is to force it into categorical buckets like age groups 18 to 25, 26 to 35, 36 plus. This reduces noise and allows you to calculate the expected value or conversion rates for distinct cohorts. So here is our an example question. Example question 6.1, bar chart versus histograms. Okay, so to understand this topic, we are going to solve this question. So the hook, the explaining the business problem. Okay, when enterprise clients start leaving your SaaS platform, customer success and product leadership need answers immediately. You cannot fix a leaky bucket if you don't know where the holes are. Today, we are going to use categorical data to answer a critical strategic question. Are we losing accounts because our product is too expensive? Because we are missing are we losing accounts because our product is too expensive, or because we are missing critical functionality, or is it simply due to macroeconomic factors completely beyond our control? So the setup explaining our dataset. To figure this out, we are going to dive into our Q3 enterprise SaaS churn data. Imagine this is the raw exit interview data pulled straight out of a CRM like Salesforce or HubSpot. Our key metric here is percentage of lost accounts, clearly segmented by their primary reason for churning. Before, we are looking at the distinct separate categories rather than continuous numbers. We have simulated a categorical dataset detailing 5 specific churn drivers: budget cuts at roughly 42%, poor onboarding at 30%, missing features at 23%, and smaller factors like our internal champion leaving or competitor pricing. Let's jump into the code and see why a bar chart, and absolutely not a histogram, is the exact right tool to visualize this data and dictate the immediate retention strategy. So let's start to code this solution. Okay, import pandas as pd, import matplotlib dot pyplot as plt. So 1, simulated data, simulated data, enterprise SaaS churn reasons, percentage of lost accounts. Okay. In a real tech company, this data comes from Salesforce or similar platform. From So let's create the churn data. Churn underscore data. Churn data equals to budget cuts 40.42.43, comma, poor poor onboarding is 30.40, 30.40, missing features, missing features is 23.02, champion left 4.03, competitor pricing 0.12. Creating the data frame. Creating the data frame. df underscore churn equals pd dot data frame churn underscore data. Hashtag 2, plotting the bar chart. We transpose the data frame to align the categories on the x-axis. On the x-axis, ax equals to df underscore churn dot transpose dot plot dot bar fig size equals 8 comma 5, 8 comma 5 comma legend equals false, color equals hashtag 2c3e50. adds color adds color equals black. Executive formatting hashtag 3 executive formatting. Ax dot set x label underscore primary reason for churn font weight equals bold. Ax dot set y label as percentage of lost accounts. Font weight equals bold. Ax dot set title enterprise SaaS churn by category, comma font size equals 14, comma PAD equals 15. Rotating the x-axis labels so they are readable in a presentation. plt.xticks rotation equals 45, comma HA equals right. Hashtag add subtle grid lines for readability. Subtle grid lines for readability. Ax dot grid axis equals y, comma line style equals dash dash, comma alpha equals 0.7. Adjust layouts so labels don't get cut off. plt dot tight layout plt dot show. Okay, let's run this. Okay, so we have our bar chart ready. So here is the primary region for churn. So when we review the Q3 enterprise SaaS churn data visualized in this bar chart, a very clear and actionable narrative emerges regarding our recent retention challenges. The dominant driver of the churn, the dominant driver of churn, accounting for over 42% of our lost accounts, is budget cuts. This indicates that a significant portion of our churn is driven by macroeconomic pressure and tightening budgets on the client side, rather than a fundamental flaw in our platform's value proposition. However, we need to focus on second and third largest factors, which are entirely on our operational control. Poor onboarding at around 30% and missing features at 23%. Together, These operational gaps accounts for more than half of all our lost enterprise accounts. Interestingly, competitive pricing is virtually a non-issue at just 0.12%. Strategically, this dictates our exact next steps. We should absolutely not discount our strategically this dictates our next steps. We should absolutely not discount our software or engage in a race to the bottom on price. Instead, leadership must immediately reallocate capital to revamp the customer onboarding program and accelerate the engineering efforts to ship those highly requested missing features. Okay, we had to answer, are we losing accounts because our product is too expensive, lacking critical functionality, or due to macroeconomic factors beyond our immediate control? So we should absolutely not discount our software or engage in a race to bottom on price. Instead, leadership must immediately reallocate capital to revamp the customer onboarding program and accelerate the engineering efforts to ship those highly requested missing features. So let's start with our topic number 7, correlation and scatter plots. The magic metric finder. Correlation and scatter plots. The magic metric finder. Correlation coefficient. This measures how closely two numeric variables move together on a strict scale from -1 to +1. In product analytics, this is how you measure your growth. This is how you measure your core growth drivers. For example, proving that a higher number of daily dashboard logins strongly correlates with a lower probability of customer churn. Okay, so here is the formula of Pearson's correlation coefficient. Visualizing the ecosystem heat maps. In a real tech stack, you never analyze just two variables. You build a correlation matrix visualized as seaborne heat map to cross-reference every feature in your dataset instantly. This is the fastest way to find hidden relationships, like realizing that weather severity perfectly correlates with delivery SLA breaches. The ground truth, scatter plots. The correlation coefficient is just a single number, and it can easily lie if data is skewed by outliers. A scatter plot forces you to look at the actual shape of the data. It is critical for spotting nonlinear relationships. For example, sending push notifications increases the daily active users' positive correlation. If you send too many, users get annoyed and uninstall the app. The trend reverses. The golden rule. Correlation does not mean causation. Just because two matrices move together, like high ice cream sales and high drowning rates in summers, does not mean one causes another. As an analyst, you use correlation to discover patterns, but you use A/B testing to prove causation. So here is the example question number 7.1, correlation in enterprise tech, to understand the concept of correlation coefficient. So the hook, here is the business problem. Imagine you are leading you are leading imagine you are leading customer success and you are getting completely contradictory feedback from your highest paying enterprise clients. Half of your VIPs are praising your team for instant support, while Other half is furious about severe days long resolution delays. Today we are going to use data visualization to answer a critical diagnostic question. Are our support refs just wildly inconsistent? Or is there a fundamental hidden structural flaw in exactly how enterprise tickets are routed and resolved? The setup, explaining the dataset. To diagnose this issue, we are going to simulate uh, I explained the wrong question to you. I am sorry for this. Please ignore this. So, here is the question number 7.1. In enterprise software, no department operates in vacuum. Yet, leadership often struggles to see exactly how different KPIs impact one another across the company. Today we are going to use correlation analysis to answer a massive strategic question for our executive team. Are our marketing dollars actually driving closed revenue? And what specific operational factors are most responsible for accelerating our customer churn? The setup, explaining the dataset. To uncover these hidden relationships, we are going to simulate a full year, 365 days of enterprise SaaS data. We will be tracking a wide variety of core KPIs like marketing spend, demo requests, new annual recruiting revenue, support tickets, NPS scores, and churn rate. We have modeled this simulation to reflect realistic business dependencies. On the growth side, you will see that demo requests are mathematically tied to marketing spend, and new ARR realized directly on those incoming demos. Over on the retention side, we have programmed the churn rate to negatively correlate with our NPS score and positively correlate with the volume of support tickets. Let's build into Python to build a correlation matrix and a heat map so we can visually prove exactly how all these moving parts are connected. Okay, we have to answer this strategic question. Are our marketing dollars actually driving closed revenue? And what operational factors are most responsible for driving our customer churn? So example. So here is the example and the code. Import pandas as PD. Import numpy as np. Import cbond as sns. Import matplotlib.pyplot as plt. Simulate 12 months of enterprise SaaS data, daily or weekly metrics. np.random.seed 42 days equals to 365. Simulating base metrics with realistic business dependencies. Dependencies. Marketing spend. Marketing spend equals np dot random dot normal 50,000 comma 10,000 comma days. Demos heavily rely on marketing spend. Demo requests equals demo requests equals marketing underscore spend into 0.05 plus np dot random dot normal 0 comma 500 comma days. ARR heavily relies on demos. New ARR equals demo requests into 1200 plus np dot random dot normal 0 comma 50,000 comma days. Independent matrices. Independent metrics. Example: product quality issues, NPS score equals np dot random dot normal 40 comma 15 comma days. Support tickets. Support tickets equals np dot random dot normal np dot random dot normal 200 comma 50 comma days. Churn rate is negatively correlated with NPS and positively with support tickets and positively with support tickets. Churn rate equals support tickets into 0.02 minus NPS score into 0.05 plus np dot random dot normal 2 comma 0.5 comma days. So we assemble the data frame. Assemble the data frame. SAS underscore data equals pd dot data frame marketing spend marketing spend is marketing underscore spend comma demo requests as demo underscore requests, comma, new ARR equals new underscore ARR, support tickets as support underscore tickets, NPS score, N NPS ratings, net promoter score, net promoter score as NPS underscores, churn rate as churn underscore rate, hashtag 3, calculate the Pearson correlation matrix, correlation matrix, correlation underscore matrix equals SAS underscore data dot core. Step 4, executive visualization, executive visualization, executive visualization, Seaborn heat map, plt dot figure fig size, fig size equals 8 comma 6, using a diverging palette, blue for positive to red to negative, V min equals -1 and V max equals 1 are critical to lock the scale for business decks. AX equals to SNS dot heat map correlation underscore matrix, V min equals -1, V max equals 1, center equals 0, C map equals SNS dot diverging palette, palette 20 comma 220 comma as C map equals true comma not equals true, FMT equals dot to F comma line widths equal 0.5 comma square equals true. ax dot set title enterprise SaaS KPI correlation matrix font size equals 14, PAD equals 20, font weight equals bold, plt dot x ticks rotation equals 45, comma ha equals right, plt dot tight underscore layout plt dot show. No module named Seaborn. Eh? No module named Seaborn. Okay, first I have to install Seaborn. Pip install Seaborn. Module Seaborn has no attribute diverging patate. Patate or palette? Palette. Okay, since Seaborn has been installed. Okay, we finally have our enterprise SaaS KPI correlation matrix. So we needed to find, are our marketing dollars actually driving closed revenue, and what operational factors are most responsible for driving our customer churn. So we have got this enterprise SaaS KPI correlation matrix. Uh, and what we can see here is that so when we calculate the Pearson correlation matrix and visualize it as a heat map, we are directly mapping out the mathematical relationships between core business drivers. First, looking at the revenue engine, our model proves a strong positive correlation represented by blue hues on the diverging palette flowing directly from marketing spend to demo requests and ultimately to new ARR. This quantitatively validates that our top of the funnel marketing investments are effectively translating into closed business. However, the critical insight lies in the retention side. We see the churn rate is positively correlated. Our churn rate is positively correlated to support tickets and negatively correlated with NPS score. In practical terms, this means that as support tickets volumes rise and our net promoter score drops, customer churn mathematically accelerates. Strategically, this visual provides undeniable data backed evidence For our next board meeting, if we want to protect our new acquired ARR, we cannot just rely on sales. We must immediately reallocate resources to our customer support and product team to drive our tickets volumes down and boost overall customer satisfaction. So we have answered this question. Yes, our marketing dollars are actually driving the closed revenue, and the operational factors like uh, increasing support tickets are increasing our customer churn. Okay, so let's move to our next question. Question number 7.2, bivariate analysis and strategic scatter plots. Example question 7.2, bivariates analysis and strategic scatter plot. So if you are running customer success or sales for a massive enterprise platform, you need to quickly segment your client base to identify immediate churn risks and hidden upsell opportunities. You cannot just guess who needs attention. Today, we are going to use bivariate analysis to answer a critical strategic question. Does an increase in product usage mathematically translate into revenue expansion? And more importantly, which specific accounts are operating completely outside of that expected behavior? Okay, to figure this out, we are going to jump into Python and analyze Q3 health data of 1500 active enterprise accounts. Because this is a bivariate analysis, we are comparing two specific matrices side by side: API usage growth versus account revenue growth. Both metrics are measured as normalized percentages. When a dead center zero represents a completely flat baseline, we have simulated this dataset so that revenue is generally positively correlated with API usage, meaning values above zero indicate healthy expansion, while values below zero indicate contraction and churn risk. Let's map these 1500 accounts into a scatter plot and divide them into four strategic quadrants so we can show our sales team exactly who to call today. So we have to answer this critical strategic question. Does an increase in product usage mathematically translate into revenue expansion? And what specific accounts are operating outside of an unexpected? Does an increase in product usage mathematically translate into revenue expansion? And what specific accounts are operating outside of the expected behavior? So we have to answer a critical strategic question. Does an increase in product usage mathematically translate into revenue expansion? And what specific accounts are operating outside that expected behavior? So let's start. Import pandas as PD, import numpy as np, import matplotlib dot pyplot as plt, simulate enterprise SaaS client data centered around 0, np.random.seed 42, simulating 1500 enterprise accounts enterprise accounts simulating 1500 enterprise accounts. Positive equals growth or expansion, negative equals contraction or churn. Growth or expansion. API usage change equals np dot random dot normal 0 comma 0.5 comma 1500. Revenue expansion is positively correlated with API usage, but with some noise. Revenue change equals to API usage change, API usage change, API usage API usage change into 0.6 plus np dot random dot normal 0 comma 0.4 comma 1500. SAS data equals pd dot data frame usage growth API usage change revenue growth as revenue change executive scatterplot execution using alpha equals 0.3 to fix the overplotting issue. AX equals SAS underscore data dot plot dot scatter. X equals true. Usage growth Y equals revenue growth fig size equals 7,7 alpha equals 0.3, color equals hash 2980b9, edge color equals none. Defining the business quadrants. Quadrants. Drawing the zero lines is what turns a basic chart into a strategic matrix. Ax dot axh line 0 comma color equals black comma lw equals 0 point lw equals 1.5 line width, line style equals dash dash ax dot axv line 0 comma color equals black ax dot set x label as API usage growth normalized percentage comma font weight equals bold ax dot set y label as account revenue growth, account revenue growth normalized percentage comma font weight equals bold ax dot set title as enterprise account health metrics Q3 comma font size comma font size equals 14, PAD equals 15, PLT dot show. Invalid syntax. Simulate enterprise sales data, line number 6. Hashtag. Okay. So we needed to answer, does an increase in product usage mathematically translate into revenue expansion, and which specific accounts are operating outside the expected behavior. So here is our enterprise account health metrics. So by plotting our 1500 enterprise accounts on this scatter plot, and drawing strict zero lines on both the axes. We have transformed a standard statistical chart into a four quadrant enterprise account health metrics. Because we apply transparency to data points, we can clearly see the dense correlation trend moving up to the right generally. As our clients use the API more, they pay us more. However, the true executive value lies in the quadrant, the top right. We have our healthy expansion accounts. Usage and revenue are both growing. In the bottom left, we have our critical churn risks. Clients who are abandoning the platform and contracting their spend. Customer success must intervene in this bottom left quadrant today. But look at the off diagonal quadrants. The bottom right represents the clients whose API usage is exploding, but revenue growth is still negative or flat. These clients are extracting massive value from our infrastructure without paying for it. The quadrant is highly qualified target list for our sales team to immediately initiate upsell and tier expansion conversion. So we have answered this question. So yes, increase in product usage mathematically translate in revenue expansion, and the which accounts are operating outside the expected behavior. The accounts, so these accounts in the quadrant bottom right are expecting different than the expected behavior. So we must, so it is the target list of sales team to immediately initiate upsell and tier expansion conversions. This quadrant bottom, this quadrant which is in bottom right. So let's move to our next topic. It is the last topic of the chapter 1, exploratory data analysis. So topic number 8, exploring two or more variables, segmentation. Contingency tables, cross tabs. The absolute backbone of cohort analysis and A/B testing. When you have two categorical values, example, we device type, iOS or Android versus churn status, yes or no. A contingency table, pivot table, instantly reveals conversion rates, structural drop-offs across different user segments, segmenting numeric data by category. In operations, you rarely look at the global average. You split a numeric metric by categorically grouping. For example, comparing delivery time minutes, which is numeric, across warehouse zones. This isolates exactly which node in your supply chain or product funnel is dragging down the global metrics. Group box plot, the executive view. Placing box plots side by side based on category is the fastest way to compare SLAs. If you plot delivery time by vehicle type, bike versus truck, side by side whiskers immediately expose which fleet has the worst outliers and widest variance. Violin plot, the product manager view. A box plot hides the actual shape of the data inside the box. A violin plot replaces the box with a density curve, showing exactly where the most users are clustered. It is highly effective for spotting bimodal distributions. Example, realizing a specific subscription tier is actually split into two distinct groups for of power users and ghost users. So here is our question number 8.1, contingency table and normalization trap. Okay, the business problem. Imagine your customer success leadership team looking at a massive list of churned accounts and completely panicking because the vast majority of those clients belong to your basic tiers. Their immediate reaction will be to divert all engineering resources to fix that tier. But today we are going to fix, but today we are going to answer a critical diagnostic question. Is our basic tier actually broken and bleeding users? Or if this is an absolute mathematical illusion caused by the sheer volume of the customer sitting in that tier? The setup. Explaining the dataset. To diagnose this, we are going to generate 15,000 simulated B2B SaaS customer records. We will be cross-referencing two specific categorical matrices: the account renewal status, meaning whether they churned, renewed or upgraded, against their account tier, basic, professional or enterprise. To make this exactly like a real world scenario, we are intentionally skewing the customer base. 70% of the simulated users are basic, while only 5% are enterprise. Behind the scenes, we have actually modeled the basic tiers to be incredibly healthy, with only a 5% churn rate, while the enterprise tier is secretly in crisis, with a severe 25% churn rate. Let's jump into Python and build a contingency table, and I will show you exactly how looking at the raw counts creates a massive strategic trap, and why normalizing your data into percentages is the only way to cover the truth. So let's start to code. Import Python as PD, import numpy as np. So for number one, simulate B2B SaaS customer data. np.random.seed42 n underscore customers equals 15,000. Generating a heavily skewed customer base, mostly basic, few enterprise tiers. np.random.choice basic, professional, enterprise. Enterprise size equals n underscore customers, comma p equals 0.70, comma 0.25, comma 0.05. Generating renewal statuses. statuses Enterprise has higher churn in this simulation. Status equals this. for tier in tiers if tier equals basic statuses statuses dot append np dot random dot choice churned comma renewed comma upgraded comma p equals 0.05 elif 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 tier equals professional statuses dot append random dot choice p equals to 1.2 elif elif else hashtag enterprise statuses dot append dot random dot choice p equals to 2.5 sas underscore data equals to pd dot data frame account tier as tiers status as statuses generate the raw count contingency table hashtag margins equals true adds the all totals column and row cross tab counts equals pd dot cross tab SAS underscore data account tier SAS data statuses comma margins equals true. Print raw counts misleading. Print cross tab counts. Print hashtag in hashtag 3. Generate the row percentage contingency table. Normalize equals to index mathematically mathematically converts counts to row percentages instantly. Cross tab percentages equals pd dot cross tab SAS data account tier SAS data status normalize equals to index formatting to look like executive percentages cross tab percentages equals cross tab percentages into 100 dot round 1. Print row percentages actionable. Print cross tab percentages. Invalid syntax lftr. Invalid syntax lf. comma, invalid syntax. Okay, so I have fixed the code. So what we were given. So we had to solve this. We must answer the critical diagnostic question. Is our basic tier actually broken and bleeding users? Or is this an illusion caused by sheer volume of user in that tier? So we have written the code. Okay. If we only look at the raw counts in our contingency table, we are going to make a massive strategic error because 70% of our entire customer base lies in the basic tier. They will naturally generate the highest raw volume of churned accounts. Okay, if we had those numbers to the product team, they will spend the next quarter trying to fix the basic tier. However, when we normalize the data and convert the table into raw percentages, the true operational reality emerges. The percentages reveal that our basic tier is incredibly healthy, churning at just 5%. Okay, the person, the real crisis is hidden in our top accounts. The enterprise tier is churning at the massive rate of 25%. By using percentages instead of raw counts, we prove the leadership that we must immediately pivot our retention resources away from high volume basic tiers and deploy an emerging intervention for our highest paying enterprise clients. Okay, so let's move to our next question. Example question 8.2. Box plots, box plots versus Violin plots, revealing hidden process flaw. Imagine you are leading the customer success and you are getting completely contradictory feedback from your highest paying enterprise clients. Half of your VIPs are praising your team for instant support, while the other half while the other half is furious about severe days-long resolution delays. Today we are going to use data visualization to answer a critical diagnostic question. Are our support reps just wildly inconsistent, or is a fundamental hidden structural flaw in exactly how enterprise tickets are routed and resolved? Okay, the setup. To diagnose this issue, we are going to simulate 1800 customer support tickets, tracking our core metric, ticket resolution time based in hours. We'll split this data across three different account tiers: Basic, Pro, and Enterprise. We have simulated the Basic and Pro tiers to follow standard predictable bell curves, averaging 48 hours and 12 hours to resolve respectively. However, we have intentionally built the Enterprise tier as a bimodal distribution. This means the data is split into two massive extremes: tickets that are resolved almost instantly in about 2 hours, likely via direct VIP Slack channels, and the tickets that get stuck in an engineering black hole for 72 hours. Let's jump into Python and I will show you exactly how a standard box plot completely hides this process failure and why a violin plot is always the only way to expose the truth to the leadership team. Okay, so we have to answer: are our support reps simply inconsistent, or is there a fundamental structural flaw structural flaw in how enterprise tickets are routed and resolved. Okay, so let's write the code for this. Import pandas as pd, import numpy as np, import cbond as sns, import matplotlib.pyplot as plt. So first simulate enterprise SLA data np.random.seed 42 basic standard normal distribution average 48 hours to resolve. Basic res equals np dot random dot normal log equals 48, scale equals 12 comma size equals 1000. Pro tighter SLA average 12 hours plus pro into 500 pro into 500 plus enterprise into 300 SLA underscore df equals pd dot data frame data. Ensure no negative times. SLA underscore df resolution hours equals SLA underscore df dot clip lower equals 0. To executive visualization visualization executive visualization box plot versus violin plot fig comma axis equals plt dot subplots 1 comma 2 comma fig size 14 comma 6 fig size is not defined. Fig size equals to 14,6. Okay. Plot A, the box plot. Plot A, the box plot hides the nuances. SNS box plot data equals to SLA underscore DF X equals to account tier Y equals to resolution time order equals basic comma pro pro comma enterprise AX equals AXES 0 palette equals blues. Plot B axis 0 axis 0 dot set title SLA box plot axis 0 dot set y label resolution time in hours axis 0 dot set x label plot B the violin plot reveals the process flow SNS violin plot SLA data DF resolution time inner equals quartile 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 AX inner one blue axis 1 SLA violin plot PLT dot show Uh, Line number 49, x0 dot available does not match the. Line number 60, so is it available does not match the. SNS dot boxplot. Could not interpret account tier for X. An entry with this name does not appear in the data. Account tier for X. Account tier for X. Account underscore tier. Account underscore tier. Could not interpret resolution times for Y. Resolution hours. Resolution hours. Resolution hours. Passing palette without assigning hue is depreciated and will be removed and assigned. Okay. Okay. So here is our interpretation. What we have to find? We had to answer, are our support reps simply inconsistent, or is there is a fundamental structural flaw in how enterprise tickets are routed and resolved? So we have generated two plots, box plot and Violin plot. So if we present the standard box plot to our on the left to our executive team, it tells a highly misleading story. It makes the enterprise tier look like it has one massive continuous spread of with a median resolution time somewhere sitting in the middle. Okay. If leadership sees this, they will assume our support reps are simply inconsistent and unpredictable. However, when we switch to the Violin plot to the right, which maps out the actual density of the data, we expose the a critical process failure. The enterprise data is bimodal. It is entirely split into two distinct extremes. Operationally, this proves that our VIP support experience is completely fractured. One group of ticket is resolved on almost instantly, likely because those specific clients bypass the standard queues via direct Slack access to their account managers. The other group hits a massive bottleneck, taking an average of 72 hours to resolve, likely because they require deep engineering intervention. This isn't a rep performance issue, it's a systematic routing issue. We must immediately standardize and expedite the engineering escalation pathway for all enterprise accounts. So our chapter 1 is over. So we will move to our next chapter, chapter number 2, soon in the next video. So let's see you all in the next video.